already made the decision. That's too late. Okay, so I want everyone to think about that. Adapting, right? Adapting. So can you see that? Okay, so that's the idea. Mathematically, what I do. Mathematically, I have to take this function. So remember what you have to do. You have to optimize this function, f of h. We have to minimize this. We have to minimize this f of h. Okay. And to minimize f of h, what I have to do here is I take the function. So minimize this f of h. And f of h, remember that loosely I can take f of h and I change them a little bit. I change them by some delta h here. Right? I change them. So you see that I have this function, I need to minimize, I need to find the minimum point. I need to find the minimum point here. That will be the h optimal. But now I'm sitting here, and I want to maybe move around, and I find the direction where I need to decrease the cost function. So I do this, and this thing here, you note that using the taker in the first order is approximately equal to f of h plus the gradient of f of h times with h. The transform here times h, and this is approximation. Right? It's like the first order expansion of the Taylor series. And there's something else. So the message here is to minimize it, you need to make this thing, measure this in the negative direction. Then you can decrease it as less as you can. Right? So that, and then if you use the delta h here, this one here equal to something is maybe equal to mu minus mu, the gradient of f of h. So this thing here is so-called the steep descent. Steep descent. Right? I'm going to move around the space h, and at each point, the next instant, I'm going to move the direction that guarantees steeply, maximally reduce my cost function. Okay, so I'm going to do that. Okay. Now, what can I put out in practice? I'm going to put out in practice. So,
sorry.
Yes.
In the first law, I think the last input delta, the first law.
Yes. Oh, thank you. Yes. Very well. Yes. Excellent point. Yes. Okay. So I reduce the thing in that direction. All right. So now how can I put it in practice? So I have f of h. Well, let's say the delta f of h. Everyone remember what it is earlier on? It is minus 2p plus r minus 2 times r of h. Right? That's the delta 2p delta. So now I'm going to make the change now. So by the that now I'm going to make the h of n plus 1, this vector equal to the first one, the h, and the one previously, plus this mu here of the delta h of n. So plus of this, so that will actually become minus mu of 2p minus 2rh of n. Okay. That's how I do it. Okay? Is there any problem? I think there's missing plus or minus something. So this thing here, I can write this is so-called steep descent, right? Steep descent here. And so that is the updated formula. The updated formula of Hn. The updated formula of Hn is that solving my problem. Solving my problem. Can I still use this now? To use this updated formula, what do I need to have? Mu, okay, I have to find mu, right? Mu is some number, and I gotta adjust. This mu the step, right? That's the direction. I know that, okay. For example, to find where is, convention center. I know that the direction I should play. And I take some step, but I have to be careful, right? Before, if I take too far, to go the other direction. So, that mu is just telling you how much you go in that direction. Okay, so mu is that steps. What else do I need to have? This thing here is what I made previously, so that's where I am. So I have this thing. I need to find out those P and R. P and R. And the P here, so the P is equal to, if you remember early on, it is expectations of this vector E of n and x of n, d of n and x of n minus 1 and so on, right? So that is the P, and similar with R. Question?
I think that in the last formula they have mu, because in delta H we have mu in
Okay. Alright, so no, yes. Okay. Yes, very good. Alright, but now the problem is to find out the P, I need to find out all those expectations. Right? I need to find out all those expectations. And similar for the R. Now, the very clever idea was done by Whittle in the 60s. He said, well, to find out this, I need to wait. Again, I need to wait. And have to wait for y to get the filter. Get y to get the filter. So simply, the LMS algorithm, one of the most powerful algorithms in signal processing. What does LMS stand for? Least mean square I hope that correct. The least mean square algorithms replace P by the P estimate, which is, I have to take this expectation. Which I have to take expectation all by the way. I just simply replace expectation with doubt. I just take the value, I write it. So I replace this by the simply dn xn, and then so on. D of n, x of n minus 1. So on. Do I know x? I do know x, right? Because that's my input. Do I know d? Yes, because that is the desired output at the previous step, right? So taking now, we have this, we put n plus 1 here. So now what we are trying to do now is estimating y n minus 1.